Now we will compute packet delay in various interesting scenarios. In the first scenario, we have two end systems, a source and a destination, directly connected through a single link. The source wants to send a 3-bit packet to the destination. In reality, there aren't such small packets, but we will pretend there are to keep things simple. When the source transmits a packet over the link, it takes a certain amount of time to push all the bits of the packet onto the link. This amount of time is called the transmission delay, and it is equal to the packet size divided by the link transmission rate. For example, if the link has transmission rate 1 gigabit per second, the transmission delay for 3 bits is 3 nanoseconds. Then it takes a certain amount of time for the last bit of the packet to reach the destination. This amount of time is called propagation delay, and it is equal to the link length divided by the link propagation speed. For example, if the link is 1 meter long and data can travel in it with the speed of light, then the propagation delay of the link is 3.34 nanoseconds. So, in the scenario where two end systems are directly connected through one link, the packet delay is equal to the transmission delay of the packet over the link plus the propagation delay of the link. These two components, transmission and propagation delay, are very different from each other. Transmission delay depends on the transmission rate of the link and the size of the packet. Propagation delay depends on the propagation speed of the link and the length of the link, but not the packet. In the next scenario, we have two end systems connected through two network links of the same properties with one packet switch in the middle. We will first assume that this packet switch is what we call a circuit switch, like the devices used in traditional telephone networks. In such networks, when two end systems want to communicate, before they start exchanging data, a physical circuit is established between them. As a result, as soon as the switch receives a bit from the source, it can immediately transmit it to the destination. When the source transmits a packet, first the source pushes all the bits of the packet onto the first link. So we have the transmission delay over the first link. Then we have to wait for the last bit of the packet to get to the destination. So we have the propagation delay of the first and second link. So in this scenario, the packet delay is the sum of the transmission delay of the packet over the first link plus the propagation delay of all the links. In a way, it's as if the packet switch is not there at all. It does not introduce any delay. Except there is, of course, the delay to establish the physical circuit before the communication starts, but we may not count that if it gets amortized over many packets. In the next scenario, we have again two end systems, a source and a destination, connected through one packet switch. This switch, however, is not a circuit switch. It is what we call a store and forward switch, which is much closer to the devices that are used on the internet today. When the two end systems want to communicate, there is no need to establish any physical circuit between them. The source starts sending packets to the destination. The switch has a queue, and when it starts receiving bits from a packet, it stores them in the queue until all the bits of the packet arrive. Only then can the switch transmit the packet onto the next link. This is why it is called a store and forward switch, because it stores the bits until the last bit of the packet has arrived. When the source transmits a packet, the source first pushes all the bits of the packet onto the link. So again, we have the transmission delay over the first link. Then we have to wait for the last bit of the packet to get to the switch. When the last bit arrives at the switch, the previous bits of the packet are waiting there. So we have the propagation delay of the first link. Then the switch processes the packet. And finally, it pushes all the bits of the packet onto the second link. So we have the transmission delay over the second link, and then we have to wait for the last bit of the packet to get to the destination. So we have the propagation delay of the second link. So in this scenario, the packet delay is equal to the transmission delay over the first link, plus the propagation delay over the first link, plus the processing delay at the switch, plus the transmission delay again over the second link, plus the propagation delay of the second link. Because this is a store and forward switch, it does not immediately transmit each bit as it receives it. It waits to receive all the bits of each packet, then processes the packet, and then retransmits all the bits of the packet onto the next link. So this introduces an extra transmission delay component, okay, the transmission delay over the second link. This may seem confusing. Why did we not have this extra transmission delay component in the previous scenario? Because there we had a circuit switch. As soon as it receives a bit, it transmits the bit. So the first bits of the packet do not need to sit at the switch waiting for the last bit of the packet to arrive. Finally, there is a very important delay component that I skipped. It is possible that when the last bit of the packet arrives at the switch is still not ready to process the packet because it is processing other packets that arrived earlier. As a result, the packet must wait in a queue even if all its bits have arrived. So to our formula, we must add the queuing delay that the packet experiences at the switch.